I'm going to go ahead and get started. Welcome, my name is John Lambert. I'm a security group manager at Microsoft. Today I'm going to talk about the security engineering behind Windows Vista and how it'll be different from every other Windows release, primarily through the integration of the security development lifecycle into the engineering process into Vista. We've worked with the security research community a great deal over the last few years and learned a lot, and this presentation is going to reflect all of the lessons that we've learned in engaging with this community. Part of what we wanted to do today was to give back to the community, share our process, tell you what we're doing, gather your feedback, tell you what we're doing in terms of the heap and other technologies like that. I hope what you'll see, what you'll think by the end of this presentation is that you'll hear that we've listened and that we've tried to take the best of what we heard and apply it to Vista. I joined Microsoft about 6 years ago. I've been fortunate enough to have what I call a front row seat at security at Microsoft for those 6 years. I was there to see the company deal with the challenges of Code Red, NIMDA, Slammer, Sasser, et cetera. But I've also seen the company respond in terms of the efforts behind the Windows stand down or the Windows security push, things like Windows XPSP2 and Windows Server 2003. Finally, the formulation of the security development lifecycle in SDL and its adoption across Microsoft. I happened to be at the meeting where we asked Bill to write what became the Trustworthy Computing Memo. It was not the day that security dawned at Microsoft, but it was really us going to Bill and saying, Bill, we need to do something about this across the board at Microsoft. We need to focus and it needs to start from the top down. I run a team inside the Secure Windows Initiative at Microsoft dedicated to helping product teams improve their products. What you'll hear in this deck today is about how we're doing and taking security engineering and how we've implemented that in Windows Vista. You'll hear about the overall security strategy and the game plan behind what we did. We'll do some deep dives onto the major security initiatives in Windows Vista. You'll hear about the unprecedented level of scrutiny that Vista has gotten by members of the security research community and some of the results from there and the things that we've learned. I'm here to take any engineering-focused feedback that you have and take it back to the product team. Just to set your expectation, this is not a presentation about security features, so I will not be talking about BitLocker or public key infrastructure or Kerberos or any of those things. This is really about the engineering process that's behind all the different features in Windows Vista. So let me start off by setting a little context. So the Security Development Lifecycle, or SDL, is how it takes all the lessons that we've learned and really integrates security through the engineering process from beginning and to end. And SDL is something that we do on all major Microsoft products, and this presentation really focuses on how we implemented SDL for Vista. We learned things during the Windows security stand down, like, for example, doing threat modeling after the code has already been written is not the greatest time to do threat modeling. And so we've taken things and integrated them at the appropriate time in the life cycle. So it starts off with security training and education. Then it moves on to security planning, threat models at design time, taking advantage of compiler hardening and code scanning tools at implementation, security testing, et cetera. So the overall game plan behind Windows Vista, we really had a really special opportunity in Vista, which is we had a chance to take all the different lessons that we've learned from security releases at Microsoft before and apply it for the first time to an end-to-end operating system release, a major operating system release. And so we could really go and retool the entire process to take advantage of all these things. One thing we did is we went and looked at all the MSRC bulletins that we had shipped, and we wanted to understand this is an interesting set of defects in the sense that these are all security bugs that somehow had gotten past our engineering process. We didn't catch it in design, we didn't catch it at implementation or testing, and so these bugs were a very interesting set to study for that reason. Went back and tried to understand how can we catch this bug in design more upstream in the process, and what tools do we need to go right so that we can catch these tools? And we took that set and actually took that feedback and changed the engineering process in Vista to apply those things. And clearly, just looking backwards is not enough. The attacks will always get better. So we also look forward at what we thought were emerging areas of threats and what we thought would be the types of attacks people would do against the new features in Vista and try to make sure we were solid against those things. So the overall security approach, the way I like to think about it is really 4 major tactics. The first is really to go take this concept of least privilege and go apply it consistently throughout the architecture of Windows. And so Vista has probably the biggest reduction in privilege level of any Windows release ever. And we've taken this concept of least privilege and applied it to applications, things like the browser, and also services. And I'll spend a little bit of time talking about that. If you work on something like Windows, the name of the game is how do you scale. The Windows code base is very large, and you need to be able to go and really scale to get any kind of consistency of result across the entire code base. And so we took techniques that we could automate, and we tried to understand all the different things that we could automate and put a tool behind them, and then wire that tool into the process. And so we can go get consistency throughout code base. So some of these things are taking our source code scanning tools, prefix and prefast, and tuning them to find buffer overruns and other security defects. These are things like taking file parsers or RPC interfaces that are commonly targeted and doing fuzzy testing across those, doing things like identifying a set of APIs that lead to unsafe coding practices, the stir copies, the stir cats, etc., and just banning those throughout the code base. And so these are things that we could just simply automate, build a tool and wire it into the process and automate. The next part was really taking security experts and going back and having them sit with a product team and put on their adversarial mindset and think about all the different types of attacks that the component team themselves might not have thought about. And this involved attack surface reviews, threat modeling reviews, really digging into the design, and also, where necessary, going and doing penetration testing. And the last part of the strategy was defense in depth. We know there will be bugs, despite our best efforts, that will get through the process. But what we want to do to as much as our degree possible is to minimize the abilities for those bugs to be an exploitable condition. And so we've done a number of improvements in terms of the stack, the heap, and other areas so that even if a bug does get through our process, we really minimize the ability to get reliable exploitation of those defects. So this is kind of the overall game plan and basically the formula for the rest of the presentation. One way to describe the changes that we've made in Vista is really to compare it with the XP development process. And the way that you could characterize the XP development process is it was by and large, security was the responsibility of the individual developer, and that certainly hasn't changed, but it really kind of stopped there in terms of they went to training, they developed threat models, they did component level testing and reviews. When they checked it into the main source tree of Windows, they had buddy code reviews, and then it's pretty much in the product at that point. There were some things that were done across the entire code base. If any bug was tagged as a security bug, there was a person whose entire job responsibility was to make sure that those bugs did not get accidentally punted or resolved as won't fix or things like that. We also did have certain tools that we would run across the code base just as a whole. So this is Windows XP. For Windows Vista, one of the first changes that we made was we tried to understand how can we prevent defects from getting into the code base in the first place. And so we instituted this concept called quality gates. And quality gates were about if there's a way to technically check the code for some kind of issue or defect or vulnerability, to go wire that check into the check-in process so that, you know, Windows has quite a large set of developers that work on it, and so it's not like there's one source branch and everybody checks directly into that. They check into their upstream branch, which goes downstream, and finally you're into WinMain, which is the main source tree for Windows. And so we can put these quality gates at various levels up, and so the code, all the defects that they can screen for, just never make it into the product. And so some examples of things that we automate through that are things like getting rid of banned APIs. So there's about 120 functions that we've said, you know what, our root cause analysis has showed us these commonly lead to security defects. About 10% of bulletins could have been prevented if we got rid of usages of these banned APIs. So we said, what, new code in the product, we'll just not we'll not use these APIs, period. And we put a technical check into the product. And so all new code that comes into Vista does not make use of these APIs. Additionally, we could have certain code scanning tools like Prefast go and look for certain types of security defects upstream. And those set of bugs, they just never made it into the product because they were fixed before the code really ever made it in. Next, we augmented what we did across the board for all the code. So yes, teams had to do threat models, but in Vista, we actually had a set of security experts go and check the threat models. And if we saw threat models that needed more help or they needed to really go think about, no, it's not okay to mitigate that threat in documentation, we really got to go do a mitigation in code for that. That was the type of back and forth that the security experts would join with the product teams and review their threat models, and if they weren't up to snuff, we would actually go help the team get them up to snuff. I mentioned things like getting rid of these unsafe APIs. That's a great thing to do for new code that's inbound, but frankly, there's a lot of old code in the product that makes use of these unsafe programming practices, and so we wanted the entire code base to be clean by the time we shipped, so we went and got rid of 250,000 different instances of stir cat, stir copy, all those 120 different functions across the code base. This was seriously just a massive cleanup effort, month to month to month, just slowly whacking away at this stuff. And the net is, new code, old code will be cleaned by the time we ship on this stuff. We also went and annotated a lot of different APIs with SAL, and I'll walk through SAL in the next few slides so you can get a sense of what it's about. But it really helps make the tools a lot more intelligent when you can add more annotations to the code base to make the tools that much smarter. As we know, things like in cryptography, attacks increase, and methods that seemed to be secure a few years ago now look weaker and weaker and weaker. And so we did a scan for all the crypto usages across the code base. If we found somebody that had re-implemented some other version of crypto, we went and made them use the official libraries. We went and understood for every version of crypto, is it being used for some security reason? Is there actually a security effect by using this crypto? And if it was a weak version of crypto, then we made them migrate to the new secure versions. The only cases where that wasn't the case was for interop with existing standards, where the standards basically said you need to use MD4, you need to use MD5 or whatnot. We also did a major effort to harden our services, and I have a deep dive on that, and I'll wait to talk about that. Windows includes code from third parties, drivers being an easy example of that. Clearly, it's not just enough to secure the code that we write. We want to secure all the stuff that ships on the DVD now that Vista is. And so we had a process for going and understanding what was the attack surface and what was the security put into these third-party components and make sure it was really up to stuff with our standards. We also improved the mitigations across the board. These were things like the compiler innovations in terms of stack protection, changes to the heap, and making sure that that was being adopted across the board. And we also did privacy reviews. So that was across all the code. We also took a look at a slice of the product that was basically on the attack surface. So this is stuff that runs with high privilege, that listens to the network, that's been a common source of MSRC bulletins in the past. And for that, we dug in deeper. So we went and took security experts and had them go look at the design and the attack surface. We had them go look at the threat models in depth. And where we saw areas that seemed weak or seemed complicated or made some very strong security guarantee or was really a linchpin of security, we had implementation review by penetration testers. If we found issues in any of these processes, we would drive security pushes in some cases, because as we know, penetration testing is not a technique you can use to go secure a code base. It's fundamentally a diagnostic technique. And so we would go take and have the team go, if we identified a pattern of defect that they were missing, we'd go educate them about the defect, then have them go clean the rest of their code base and make sure they did that. We also went after network and file parsers, and I'll talk a little bit about that. So the first part here is really, we wanted to understand how we could go and improve the architecture of Windows and not just deal with security issues bug by bug by bug. And so if you kind of think back to earlier versions of Windows, everybody ran as administrator largely, all the services were running as local system, and so that any compromise, any flaw in any of these processes, it was basically a fatal compromise for the system. And so we wanted to address that in a couple of ways. First, we wanted to take the concept of least privilege and apply it to applications broadly. And you'll see this in the form of, we took the standard user account and enhanced it so it's a lot more functional and basically removed what many customers consider just deployment blockers in trying to move to the standard user account. The second thing is that we reduced the privilege level of admin applications so that when people do log in as administrator, not all of their programs run with all of their privileges and all of their capabilities. You know, the calculator doesn't need to take advantage of the fact that you're an administrator and have the debug privilege and whatnot, and so only administrative apps have administrative privileges. And then we even took some applications on the attack surface, like the browser, and compartmentalized it even further by putting heightened restrictions on it. The next part of what we did is we went after services, and I'm going to walk through the service hardening effort that we did in Vista. So one thing that we want to do is services have always been a point of attack in Windows. They're a point of attack because they're running all the time. They typically run with high privilege. If you're able to attack it, you don't need to wait for the user to do something to pull off your attack. And so they really have been the target of many different attacks over the past few years. So we wanted to see what we could do to reduce their privilege level and compartmentalize them. So if you do take advantage of one service, if you do take control of one service, you can't spread easily, and that doesn't automatically mean a system compromise. So the first thing we did is we wanted to get services out of local system. I mean, if you have, no matter what you do, if you have a compromise in local system, it's game over in Windows. And so we wanted to get them to these low privilege accounts, local service and network service that we had introduced in Windows XP. A local service and network service, if you're not familiar with them, are additional service accounts, but they're dramatically less privileged than local systems. So for example, they're not members of the administrators group. They don't have all of the really super powerful privileges in Windows like TCP, create, token, debug, and all those different privileges. And so they really are closer to a standard user account. If you just compare Vista to XPSP2, 8 system services that used to run as local system now run as local service, and you can see the list over there. We also took 4 services that used to run as local system and dropped their privilege level, and now they run as network service. Furthermore, for new services in Windows Vista, we saw adoption of these low-priv service account consistently across the board, and almost half of them take advantage of a low-privilege service account. So this is really taking Windows services and dropping the privilege level among them dramatically. So that's the first part of service hardening. The next part was, many times services have configuration information that's specific to that service, and it's not really information that should be shared or accessible by just any other service on the box. And so we introduced this concept called a service SID. It's just something that's implemented in Vista, and third-party applications that run on top of Vista can take advantage of it as well. But what it means is when your service starts up, you get an additional SID injected into your token that is a SID uniquely identified with that service. If you have multiple services in a service host, you get a SID for each one of those. Now what you can do with that SID is go use it in access control. And so for example, you can take, if you're the DHCP service and you have DHCP information in the registry that's really only meant for the DHCP service to modify, you can now go ACL that information to the DHCP service SID, and if another process is compromised, local service or network service, it doesn't have ACL permission to modify those resources. The next thing we introduced was a way for services to declare what privileges that they needed, and for the service control manager to automatically strip all the unnecessary privileges from their token. And so there's APIs that people can call to say, here's a set of privileges I'm going to use. If you have multiple services in a service host, the service control manager takes a union of those and puts it in there and strips away all the rest. Another thing you can do is we wanted to take services and really try to confine them down to their expected behavior. And so one of the ways that we did this was by putting network restrictions in. So if you have a service and the only thing you do is listen inbound on port 123, you can describe that and implement it, and it will be enforced by the firewall. And so if that process is compromised, that process won't be able to make outbound connections. And a lot of these restrictions and improvements that I've talked about are really process-wide. And so to really take maximal advantage of these things, we needed to go reorder and regroup the services in the shared service host of Vista, because even if you have 29 services in the service host that don't need TCP and one of them does, then they all get it. And so we went and reconfigured them, and you can see here there's a variety of different, basically flavors of service host processes that have various restrictions. And so if you have a service that you don't need network access and you can run as local service, you run in the local service no network service host. There's also varying flavors of things that have services, either network service or local service, that have a restricted set of network behaviors, or in some cases very restricted access to write to the file system, just very particular directories, but not broad rights to access the file system. And here's an example of the DHCP service in XPSP2, which was quite a big security effort by Microsoft, compared with the DHCP service in Windows Vista. So it used to run as local system and now runs as local service. It used to have 24 privileges by default, and now only has 4. It used to have a network identity, and what that means is that service could go authenticate on the network as the machine account of that box. And that allows it to basically have an authenticated user context, which, if that process is compromised, now it can go attack any other host on the network that needs an authenticated account. In Windows Vista, it doesn't have any ability to do that, so it goes off the box anonymously. It uses a fixed set of ports and also takes advantage of the service SID to compartmentalize access to the data that's unique to it. Automating proven techniques. So this was really about taking techniques that we know work, that we know can find security defects, and wiring that into the process and running those across the board. So I want to spend a little bit of time talking about SAL. It's the standard annotation language. And this is really a big technology that we use to improve the ability for tools to find defects. If you think about it, tools can only find so much information by just looking at source code. So for example, if you take a very simple line of code that says, assign this element of this array this value, is there a buffer overrun, buffer underrun here? You really don't know unless you know what the size of the buffer is and what that particular value of the array index is. And so the problem is that C and C++ code really doesn't have any way to easily identify that. SAL helps bridge the gap by allowing developers to annotate relationships between things and saying this element of this structure is really the size of the rest of the structure, or this second parameter is really the number of elements in the array that's passing the first parameter. It's not a brand new concept. If you've used RPC before, you're very familiar with these kind of concepts through IDLE. But what we did in Vista was we took all of the public APIs, added these annotations, and now when you run these tools against it, bugs will just pop out of it much easier than before. So this is kind of an example of how SAL works and how applying SAL. Imagine you have a very simple function that takes a buffer, takes a number of characters in that buffer, and then just fills that buffer with a character that you supply. Now clearly if the size of the buffer that you pass in doesn't correspond to the real size of the buffer, this thing will just walk up the end of the buffer and you have a buffer overrun. In Vista, if this function was there, a developer would see it and say, I have a string buffer, that means I need to annotate this function with SAL. The second parameter has a relationship that's involved with the first parameter. It says how many characters to write. So after they finish SAL annotating, it would look like this. And what you see in blue there is essentially a set of macros that the prefast and prefix tools will use when it analyzes the function. And let me walk through what this annotation is basically saying. So what it says is, the underscore out, that's the prefix in the annotation. What that says is this buffer needs to be non-null because this buffer is going to be written to by this function. The second one is there is a length parameter. There's a length that this buffer has a fixed length, and that length is passed in by the CCH buff second parameter. And furthermore, that length is an element count, which means a character count in this case, versus a byte count. And this indicates which parameter actually communicates that length. So here's an example of security vulnerability in a very simple program and how these annotations can help tools find these issues. If you have Visual Studio 2005, it has a version of prefast built into it, and you could take this code, compile it in there, and what the compiler would tell you is, first of all, that there's a buffer overrun accessing the first parameter buff. The writable size is only 200 characters or 400 bytes, but actually 420 bytes might be written because this program was compiled for Unicode. So it tells you right away there's a buffer overrun here. The second one is, you can see there's a call to malloc, and this program doesn't check if that returns null or not. It just passes that value right into the function. And so it's telling you, it's finding a violation of the SAL constraint that says that buffer needs to be non-null in all cases. So here's two security defects that were found just in this particular code by putting a very simple annotation into it. And if you think about it, we're applying this to all of the APIs in Vista. So everybody that writes code on top of the platform will get the benefit of the smartness that these APIs allow the tools to be. So I don't know how many of you remember this buffer overrun. This was shortly after we shipped IE7 Beta 2. There was an advisory put out by a vulnerability researcher that says if you construct an HTML page that has it, you have a stack buffer overrun in IE. Workaround is documented by the finder. The net issue was there was a particular function path create from URL that had a buffer overrun in it. When a number of the people on the SWI team saw this vulnerability report come in January, after all of our efforts in Vista so far, this was pretty much the reaction of the people in our team. But it turns out when we went and looked behind what was going on, this bug had actually been found by Prefast 2 months earlier. And it was sitting active in the bug database of Vista, ready to be worked on. Hadn't been fixed yet because it was just a beta going out the door. Hadn't been fixed yet, but it was sitting active in the bug database. And what I'm going to show you here is number one, how SAL helped us find this defect. And all of the text that's in this bug was automatically entered by the tool. So this is not a pen tester going through and saying, here's what's going on. This is the power that these tools have. So the first one that it says is there's a potential overflow using this particular parameter. It says it doesn't see anywhere where the size of this buffer is constrained in any way by the code. There's no if check that says if it's less than blah, blah, blah. It just says it looks like it's just passed in. The buffer is of max path, which is 260 elements. But the SAL contract requires that there be a relationship between the buffer size and the buffer length that's passed in. And it doesn't see how that's indicated, and so it's telling you that there's a buffer overrun here. So we kind of look at this and we think, well, did SDL really succeed or fail in this case? So if you really walk backwards a little bit further, the first thing is, after the Zotob worm came out, that exploited a vulnerability in the PNP RPC interface. After we looked at the coding construct used behind that particular vulnerability, we realized our tools didn't find it, so we added that particular pattern to Prefast and said, now it'll emit warning number 2015 when you run that tool on the code base. We changed our process to actually auto-file bugs based on that warning number. that IE bug, because of the SAL annotation, was caught immediately, and if we hadn't SAL annotated all these different functions, we wouldn't have found this defect. Furthermore, our internal fuzzing efforts reproed this exact issue just 8 days after the vulnerability report. When the browser crashed, users started sending these crash reports to Microsoft. Any crash report that comes to Microsoft that's caused because of a security defect, because the /GS flag terminates the process or what have you, security engineers and product team members go look at those on a priority basis and try to understand, these are potentially real buffer overruns touching a customer in the wild. And so we went and actually found this exact bug through that channel. So we had 3 different ways to find this bug through the Vista process. So was I happy that we didn't have it fixed by beta? No, but I really think we would have had this bug fixed by RTM. The next area. So if you've been paying attention at all, you've seen that there's really been a very sustained attack going on across the board, not just Microsoft, but especially on Microsoft applications, targeting of parsers. And so it's not that you just go to a web page and it has a malformed JPEG and you get owned, or a bitmap, or an AVI movie file, or an animated cursor, or a font. It's really across the board. The volume of attack here is really quite incredible. And so we went to Jim Alton early on in the process, and we said, if there's one thing you do in Vista, you have to get this parser story cleaned up. And so we embarked on a multi-pronged initiative to do that. The effort started by automating absolutely everything we could. So we have internal fuzzing tools that we think are as good as the external fuzzing tools. We took these tools and we identified all the different parsers that are on the attack surface for Windows and ran these tools against them. I think now we're up to 110 million different manipulations of files that are being run through these parsers and whatnot. For high-risk parsers that were particularly on the attack surface, particularly exposed, we have this extension to our fuzzers called DDL, or Data Definition Language. And what this allows you to do is to explain in an XML syntax more about the structure of the file format that you're going to fuzz. And this acts as additional intelligence and information that the tool can use to more intelligently target and fuzz the file format. And then for particularly hard targets, things that have a very complex format, things like EMF and HTML, we went after and developed smart fuzzers to go after those. In some places, we took this concept of code coverage. Clearly, it's not enough just to fuzz a particular parser. If you don't get any feedback from your fuzzing process, you really have no idea, are you just bouncing off the surface because of a checksum, or are you really getting deep into the parser? And so code coverage was one way we measured exactly what blocks and how deep were we able to go get in these parsers. Another way that code coverage helped was to make our fuzzing just that much more efficient. So for example, when we went to go fuzz JPEGs, we said, give us all your JPEGs, come one, come all, and we had a library of 19,000 different JPEGs that were the input to the fuzzing process. We went and analyzed the code coverage, the functional code coverage that these JPEGs got, and we actually were able to collapse this 19,000 JPEGs down to 47 JPEGs that gave us the exact same functional code coverage as all those 19,000, and then went and put those into the fuzzing process. And what that allows us to do is be that much more efficient about the fuzzing that happens. The second one was, fuzzing was really the first part. Fuzzing was something we did across the board. If a target was particularly difficult or it had multiple issues that surfaced, we went and applied security experts to go do a security code review and detailed program analysis on it. And so they would actually have a method using SAL to annotate the entry point to the parser and then iteratively go through the set of function calls and declare where that input was validated. And so now you have an attack path in the code base. And the tools, what we could do with our tools is crank up the noise level like never before to go analyze the set of code in this attack path. And this is, we could crank up the noise level to a level that was, frankly not sustainable code base wide, but for an attack path was. And the other thing we could do was take our mitigations and emit them more aggressively in the attack path for these parsers. So the third part of the strategy was to go take security experts, members of the security research community and internal product experts on security, and go apply them to the attack surface of the product. So we started off with feature reviews. So we prioritized all the different features of Windows Vista by risk. So we looked at what's on the network and what takes anonymous input and what makes security guarantees and what's had a history of bulletins and whatnot before. And we prioritized that list and had a feature reviewer go and sit down with the team, or in some cases multiple feature reviewers, and look through their threat models and look through their design and their attack surface, understanding were they using these concepts and doing it well. And if there was an area that was weak, we went and referred it to penetration testers for deep inspection. We augmented, as I mentioned, the internal reviews with security consultants. There was really an unprecedented amount of security review by external security consultants on Vista across the board in Windows Vista. We tried to pair up their particular expertise with the components that they were reviewing. Each of those security consultants had a Microsoft full-time employee who was their driver, and this person would act to unblock them if they got stuck, help them with the overall Windows machinery and the Windows process, and kind of help them be more fluid through the system. So feature reviews, if feature reviews are kind of, you go to the doctor and he gives you a basic checkup, penetration testing is more like a body cavity search. When I used to talk about this, I used to call this the largest pen test in history, and people that used to work for the government would remind me it's the largest commercial pen test in history, We have an internal team of hackers. I don't know, you may remember the LSD folks, Last Stage of Delirium, that discovered the flaw that the Blasterworm exploited. Those are people on my team and are members of this internal pen test team. We also have multiple simultaneous pen tests going on, so not just stuff that we were coordinating, but other things that teams had taken it upon themselves to go get pen tested. Monasano looked at the NetIO stack, for example. And then we had what we call our Blue Hat hackers. And so Jim Alchin gave them this name in some press article. They really hated it, and so naturally the name stuck. And these were over 20 different security consultants, basically in one or two rooms. And it's really like kids in a candy store here. They had full access to source code, full access to private symbols, specs, threat models, the whole thing, access to product development team. Every question they ever had could be answered within a one building radius of where they were. I mean, if you think about it, if you go and pen test Windows Vista, if you have a question about the kernel, the stack, the heap, the service, RPC, decomp, all that stuff is really within about 300 feet plus or minus where these guys are. The basic approach here was we went and selected targets based on a variety of different inputs. One of them was things that came back from the feature review process as needing further scrutiny. I kind of mentioned this earlier, but it's an important point that penetration testing is fundamentally a diagnostic process. You will never take pen test and go secure your code base with it. It can only tell you kind of as an instrument what is going on and identify a pattern of defects or a set of assumptions that were potentially dubiously made. And then you have to take that information, fix whatever bugs it finds, but then drive remediation in the engineering process to go improve that. And so they'd spend anywhere between a week or 2 months depending on the complexity and the size of the target. And one thing about pen testing Vista is absolutely nothing was out of scope. So for these guys, this was quite a bit different than normal penetration testing that they do for other customers or even other components inside of Microsoft where they say, you know what, I really don't want you to find bugs over there. I really want you to find bugs over here. And if there are bugs over there, I really don't care. I want you to find bugs here. In Vista, it was go everywhere and find all the bugs you absolutely can. So that was really a neat experience for them. This is some sampling of the findings that were found through this process. One thing we found is that the process tended to yield what we call rabbit holes. And what I mean by this is you sit down with a team and you start to whiteboard their component, and it turns out that component's actually not that interesting. But they have this dependency on a component, and that dependency is really interesting. And so this kind of iterative, recursive, kind of drilling down through dependencies is something that would happen quite often. The next kind of thing that these consultants would find are contradictions in assumptions, things that couldn't possibly hold valid. So, for example, in one threat model they found there was a component that took data off the network. It didn't actually parse that data, do anything particularly with it. The data was actually fully opaque to it, and it just passed it off to the next guy downstream. And so it said, well, we don't have to do any particular hardening or what have you, because we actually don't do anything with the data. The next component of the line says, we get our data from a local system service, and obviously he's not going to try to hack us, so we don't have to do a lot of validation on the data that we get. Clearly somebody's got to do the security work here, and so this is the kind of inter-team or inter-component dependencies that would surface through this process, and we'd say, okay, somebody's got to do the validation here. Another thing they would find are what I call process handicaps. These are things that in a large release, somehow a product team or a component team ended up getting disempowered because of the overall process or because of the cycle or what have you. And so, for example, a small team who wants to make what to them is a very large change might say, well, geez, I don't know if I can go to the Windows ship room and get them to support making this change at this late stage or right before beta or what have you. And we said, no problem, we'll talk to the ship room guys and get them to approve it. And so this was a really nice partnership that we had where teams that ordinarily would have maybe a small voice or have difficulty fixing things, we could actually go help them and drive these things and get them fixed. We'd also encounter what I call failures of imagination. There was one particular case where a component had a particular attack there was a man-in-the-middle attack on their component. And they thought, well, this attack is really complicated. You'd have to somehow get packets at the right time and really be at the right place to actually, exploit this. And so we don't really think it meets the bar for fixing for Vista. And we said, this absolutely has to be fixed. Some of us lose sight that all the people in this room, we're all versed with security. We deal with it on a regular basis. And the developers at Microsoft, though all of them go through security training, maybe the focus on their job is making it so that blind people can use the software. Or people that cannot hear can use the software effectively. And that's really what they think about first and foremost in their mind, their customer and how to do that. And so they're not exposed to all of the, the Metasploit talks and all the other great talks here. And so these failures of imagination are a thing that we would encounter. And so one great thing that we got out of having the security consultants here, where Chris Padgett and Dan Kaminsky went to this team and gave them all of the software that they could use to repro a man-in-the-middle attack. And so they gave them a server and what have you. And while this conversation between myself and the team was going on about this bug, the product unit manager for that team comes back to me and says, you know what, we took that repro and demo code and we reproduced it in our lab, and it turns out that man-in-the-middle attacks are really easy to pull off. I don't think they should be this easy to pull off. Of course we're going to go fix this bug. And so not only did we get the bug fixed, which is great, but it was really a nice collaboration between helping really open the eyes of a team to something that they thought was hard or complicated or they didn't understand in a concrete way and show them in a very personal way. We got an email from a friend of the SWI team, if you will, Matt Conivore, who installed the earlier beta of Vista and said, I noticed there's this file on my system that has owned in the title of it. Is this for real or did I just get rootkitted right away? And we went and looked, and sure enough, there is a DLL in Vista that has owned in the title of it. And we went back to the team and said, what is this about? And they kind of looked at us rather quizzically and said, well, it's the WinLog on Session Viewer window hook DLL, of course. That's, of course, the name we would put with the DLL. This was something one of our code auditors found in the code base, looking at the code. This is what he had to say about it. This was found by Felix von Leitner. The funny thing about this code is there's not a single security defect in this line of code. Unfortunately, it took Felix like 2 to 4 hours to figure that out. And Dan Kaminsky, he went to the product team during one of the talks. He says, please, please do not write code like this. Please, please. It's a DOS attack against the code auditors. A couple of them wanted to really spend their time looking at legacy code in the product. So they said, what are the different ways we can easily identify legacy code in Windows? And so how do you identify code that's been around? And Chris Padgett or Dan, I can't remember which one, came up with the idea of, if we can find old copies of MSDN, like 10-year-old copies of MSDN, obviously that's really old stuff. And if that's still in the product, we really want to go look at it. So it turns out at Microsoft, it's not that hard to find old copies of MSDN. So they just basically called up MS Library and they shipped them every copy of MSDN since 1995. And there were some howls down the hallway when they started looking at the Windows 95 SDK, and this is one of the gems that they found. This is safe stir copy circa 1995. So we've come a long way here, a long way. The last part of the presentation is really about defense in depth. And so, as you can see, we focused on changing the architecture where we could. We went and automated everything that we could. We applied security expertise. And then finally, we know there will be defects that make it through the engineering process despite our best efforts. Attack techniques always continue to improve and find things that we weren't currently aware of. And so we wanted to embark on an effort to to try to reduce the reliability that even if a security bug is there, to either prevent it from being able to be exploited because the firewall is on by default, for example, or to do things like add various cookies and mitigations so that even if it's there, your ability to successfully and reliably exploit it is much reduced compared to past operating system releases. So, for example, one of the things we did, we've shipped this /GS compiler flag in Visual Studio for a few years now, and we shipped the first version and it was worked around. We shipped the second version and it was worked around. And so during the WIDBE release of Visual Studio 2005, we had penetration testers go and sit down with the engineers on the compiler and actually pen test and write exploit code and try to figure out all the different ways that we could go improve that flag. That improved version of GS is being compiled consistently across the code base in Windows Vista. The second thing is we went and the heap was largely rewritten in Windows Vista for a number of reasons, certainly with security in mind. And I'm not going to talk about the different changes. If you really want to dig into the heap, go to Adrian Marinescu's talk later today, and he's going to explain all the different changes in the heap. I will though, talk about one of the specific changes we drove across the code base, which is because of the new architecture of the heap, it has new ways to detect when corruption has occurred. So there's control structures that are overwritten or what have you, or cookie values that don't match anymore. And so the question is, what does the heap do when it detects one of these corruptions? And so the obvious answer is, well, just go terminate the process and take it down. And it turns out if you just go turn this on for every app that runs on Windows, a lot of apps just happily corrupt their heap on a regular basis and continue to eke on and function. And it may be the 10th time, the 12th time you start up the app and you're in the middle of your document or what have you, reading your email, and the app goes away and you have no idea why. It's because it's somewhere along the way it blew its brains out, it didn't realize it, and it was getting along just fine. And so what we did in Vista was, we have this option called Heap Terminate on Corruption. For 32-bit apps, we went and basically turned it on for the entire operating system. For 64-bit apps, this was actually a nice point of differentiation here. So unlike 32-bit apps, on 64-bit, we don't have an app compat problem. We don't have a huge legacy of installed applications on 64-bit yet. And so we can make different choices about security to go set kind of a better precedent for security on 64-bit. So for example, NX is on by default for 64-bit systems and all 64-bit apps. Heap Terminate and Corrupt, if you're a 64-bit app, it's just on, third party or not. And so this is something that, like I said, this is a differentiation that we can make to go improve the overall security. Another mitigation we introduced was function pointer encoding. So if you find a security vulnerability and you're trying to exploit it, one way you get your code to run is you go bash a function pointer to point back to your code. And so one technique that we introduced was to go encode, an ability to go encode function pointers with cookie values. So when you set up your function pointer, you XOR it with a cookie that is either per process or per boot. And now when the attacker, when he goes and smashes your function pointer, he's got to somehow choose a value that is going to point back to his code after a successful XOR decoding of the cookie. And so it really makes his chances of predicting that much, much more difficult because it's different either per process or per app or per boot. When I looked just at beta 2, there was over 300 instances of usage of this function pointer encoding, so it's really being applied fairly broadly in Vista. Some of the routines you may be familiar with are listed below. So NX is something that we introduced capability for in XPSP2. The default mode is that applications and services opt into it. So all the services in Windows Vista are opted into supporting NX. One of the nice things about the fact that Vista requires beefier hardware is all the new hardware that will come out to support it is going to basically have native NX support in it. So it's a nice change from the past. And customers can take Windows and put it, basically opt everything in despite whether the app wants it or not. When NX first came out, the SWI team, we really didn't jump up and down about NX. It's a great step forward, absolutely, but we know there's attacks to circumvent it. There's these return to libc attacks and whatnot that can circumvent it. And so by itself, it's not a complete mitigation. And actually, all these mitigations by themselves are not complete in and of themselves. There was a nice paper written by Skywing and Matt Miller about bypassing data execute protection. And one of the things they noted in the paper was that one helpful complementary technique to data execute protection was address space layout randomization, to move things around in memory to defeat these return to libc attacks. And so in Windows Vista, we implemented ASLR. Like I said, it's a powerful complement to NX. You really need both of them to actually get anywhere. The final design is still being tweaked, but the way it is going to work is a DLL or an XE will opt into ASLR, and so certainly the operating system is going to be opted in, and people will be able to get a QFE from the compiler team that'll have a new flag so that they can take their application and opt them into ASLR. It's essentially just sets a bit in the PE header. The main design challenge that we had to face with ASLR is there's a trade-off between how much randomness you want to have with the addresses of your DLLs in memory and how much contiguous virtual address space that you want to have available to an app. And so the more you fragment the address space and increase the randomness, the smaller contiguous ALEX you can do. And the net might be you run SQL Server, and you know what? It can't run like it used to because it can't get that same huge virtual ALEC that it used to. And so this could cause application compatibility. So we chose a design to try to maximize the entropy here, but also try to maximize the amount of contiguous virtual address space. The net on it was there actually was not any big hiccups by introducing this into the OS, which was a bit of a surprise for us. The performance guys looked at it and they said, you know what, performance isn't going to be a problem. In some cases, you get small wins because of the particular design we took where part of the virtual address space is compressed. And there's some minor losses in corner cases, but by and large, perf is not going to be a problem here. We took 600 of the top popular third-party applications and ran them through an application compatibility test suite with Vista. None of them failed because of ASLR. So we think this is actually some really great stuff here. And so in closing, I'd like to compare, I thought this was an instructive way to walk through all the different efforts and all the different improvements that we've been making in the operating system through SDL. If you look at the Zotob worm, which was, as I mentioned, a vulnerability, a remotely exploitable vulnerability in an RPC interface. And you think about that, if you haven't heard of Zotob, that's good because Zotob was the next blaster. It really was. Same kind of buffer overrun and the same kind of service. And the reason it didn't turn into as big a deal as Blaster is because while in Windows 2000 it was remote and unauthenticated, which basically means game over for you, in XPSB1 that interface was made authenticated. And so while you could still have a worm that circulated within a corporation, you couldn't go and bridge corporations because you couldn't authenticate outside of the space where you can authenticate. In Server 2003, that interface was made admin only, and so essentially there was no remote vector. That improvement, that security callback, was backported to XPSB2, and even if we had missed it in XPSB2, the firewall was on by default and blocked it. Now imagine that vulnerability was still present in Windows Vista. So in Windows Vista, we've taken and improved prefix and prefix code scanners to recognize a much broader array of common coding patterns, and use SAL to help it find those defects. Even if that failed, we did RPC fuzzing and penetration testing of RPC interfaces to go after and find these defects. And even if that process didn't find that particular defect, we have the code is protected by an improved version of /GS and SafeSEH. Even if that failed, services are opted into NX by default and are using ASLR. And even if that failed, it's still blocked by the firewall that's on by default. There's a bunch of other talks coming up. Go see Abalade's talk on the stack if you're really interested in what we did there. Noel is talking about Wi-Fi and wireless. Adrian's got a talk on the heap that's really great, and Rob's going to be talking about IE7. And with that, I'm going to close it. I thank you for your time and your attention, and I'll be at the Microsoft booth to answer any questions that you have.